We have seen what resistors are, how they work, and how to read them. But what do they actually do in a real circuit? Resistors are everywhere. They quietly control and shape electricity in almost every electronic device around you. For example, take a small motor, connect it straight to a battery, and it runs at full speed. Add a fixed resistor in series and the speed drops. Replace it with a potentiometer and you can smoothly turn the knob to make the motor run faster or slower. This is why motors in fan and other devices use potentiometer to control the speed. Resistors are also used to divide voltage. Two resistors connected in series can split the voltage into smaller parts. This is called voltage divider. It is like a simple tap that gives you just the right amount of voltage where it is needed. In digital circuits, there is something called pull-up and pull-down resistors. They are small resistors connected to microcontroller pins to keep them steady at a known logic level. If a pin is left unconnected, it begins to float and pick up random noises, causing it to switch between 0 and 1 on its own. This can make the circuit behave unpredictably. LEDs might flicker, motors could start on their own, or sensor readings may jump. A pull-up resistor keeps the pin high when nothing is passed, and a pull-down resistor keeps it low until a signal arrives. They make sure the MCU always starts clean and stable. Resistors are also used for biasing transistors. They create the steady voltage and current that keeps the transistor in correct operating region, allowing it to amplify signals cleanly. Usually a small base resistor or a voltage divider network feeds just the right amount of current into the base, while other resistor at collector and emitter keep the point stable. Without this biasing setup, a transistor may stay off or turn fully on and the signal would get distorted. With biasing, the transistor works in balance, ready to amplify sound, radio waves, or data signals accurately. When a resistor works with capacitor, it can form a filter or a timer. From audio circuits that shape sound and in timers and clock circuits that keep precise timing inside microcontrollers. In many circuits, signal needs to be shaped before they move to the next stage. This process is called signal conditioning. Resistors help control the strength of the signal. They can reduce the voltage, limit the current, and keep the signal stable. This ensures the next part of the circuit receives clean and safe input. Sometimes the heat created by resistance isn't unwanted. It's exactly what we need. In heating elements, coil made from resistive wires convert electricity into heat. That's how electric stoves, toasters, and hair dryers produce heat. Modern electronics brought their own trends, and resistors have evolved to match them. Smaller in size, smarter in design, and built for speed. Most new devices now use SMD resistors, tiny flat chips that machines place directly on the board. This lets manufacturers assemble millions of parts automatically with speed and precision. In very sensitive instruments, precision resistors are used. They are extremely accurate and stable because even a small variation can change the result. In many modern microchips, resistor isn't a separate component anymore. They are integrated into the chip itself, so everything fits into smaller, more efficient space. Resistors are everywhere, small and silent parts that quietly keep the flow of electricity under control. From the earliest experiments to modern circuits, their job has stayed same: to manage the flow and protect what matters. In every circuit, there is a moment of balance, a pause where energy is held back, shaped, and guided. That's where the story of resistance begins. A single simple part turning wild electricity into something that can be used. Beyond it waits an entire world of components, each with its own purpose, each defining what comes after. The journey continues.